So far we have taken 2 quizzes, and probably the third quiz on November 22nd. It's going to be another 2-hour quiz. And the topics for the third quiz is whatever we covered until the last quiz. Then I think the last quiz was about up to the control integration, right? And we have briefly reviewed the differential equations. For the next several weeks, we are going to cover partial differential equations. Which was not actually included in the syllabus, but I think it's a very important topic and could be beneficial for you to know a little bit about this. The partial differential equation is a differential equation. Definition is involving partial derivatives. Partial x, partial y, etc. And this semester, we are going to cover only two-dimensional case. Only two special dimensions. The reason why we are going to cover only two special dimensions is relatively simple. Simpler that way. And it's a really difficult subject and involves many tricks. So, for example, partial t, partial u, xt, c, u, xt, partial x, partial u, xt, partial x cubed, uxt is equal to 0. This is one example. It has a name. Is this called Gopster? Drag to free equation. It involves nonlinear waves. So before we solve this equation, we make us a little bit let's say psi x minus 80. This is called psi. It's a Greek alphabet. You probably know some of that, right? Alpha, beta, gamma. You know those three, right? Delta, epsilon, iota, eta, zeta, psi, tau, sigma, psi, omega, what else? There are 24, etc., etc. Lambda, of course. Lambda. Nu, mu, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17. There are 7 more, etc., etc. So then and we assume that the solution u xt is of the form u psi. This is actually a very big assumption. But this goes back to free equation is a nonlinear wave, and so we can assume that as psi is a propagating wave. Copy, delete, paste. And I can move this. And since I have assumed that psi is x minus at, we can use a chain rule that partial t partial u xt is t psi d u psi partial t partial psi, right? And if we differentiate psi with respect to t, what do you get? Minus a, right? So if we differentiate psi with respect to t, you get minus a, right? So it becomes t psi du and minus a. How about x? partial x partial u xt partial x partial u psi d psi d u psi partial x partial u psi, and this is, if we differentiate the psi, you get 1, right? In this case, you have minus a. So this is basically d psi du. Then partial x cube is ordinary derivative. Then our equation becomes minus a d psi du psi plus c u psi d psi du psi d psi cube equal to 0. And of course, we have assumed here, we have assumed this is a very big assumption. And basically, that's what you usually do when you take you must have taken 수능 시험, right? And there is a problem that you don't know the answer. What do you do? And if you can solve the problem for 수능 시험, what do you do? You try something that may be easier, or you just throw your pencil, right? It's called educated guess. So educated guess. In Korean, usually say 찍는다, right? Or 추측한다, 찍는다. So we just assume the educated guess. Then we found that we start with the equation, which is a partial derivative with respect to t and partial derivative with respect to x. So that's definitely partial differential equation, right? But after we made the educated guess, what do we get? D psi, D psi, D psi. Ordinary differential equations, right? But it's not typical ordinary differential equation because we have u again copy, delete, and go to the next page. Paste. You can move on. So we made a bit of achievement that by making uneducated guess, we have transformed Corte back debris equation, which is a partial differential equation, into a nonlinear ordinary differential equation. Ordinary differential equation. So we make one step to simplification of the problem, that we start with the partial differential equation, which involves t and x, right? Which is very difficult to solve, I guess. But by making an educated guess for the argument to change the size, we were able to transform that partial differential equation into a ordinary differential equation, but which is not very simple because it is non-linear. But we can, there's one trick we can use. U psi d psi can be a little bit simplified. 1/2 d psi d u square. Right? So we have minus a d psi c over 2 d psi d u square d psi cube d3 u psi equal to 0. Which is a little bit simplified. Maybe I need to make a copy again from next page. Copy. Okay. So what you can do? We can reduce the order of the derivative by 1 by trying to integrate. So we integrate over psi. Then we get what? Minus a u psi plus c over 2 u square psi plus t psi square d square u psi equal to some constant, but let's put it 0. Just put constant into by 0. So we transformed into the equation into second order differential equation, which is still nonlinear, right? So what do we do? Another educated guess. So actually you need to have a lot of experience in playing with derivatives to do this. That is, C multiply by t psi du and see what happens. So minus a u psi t psi du plus c over 2 u square t psi du plus t psi square u psi t psi du. This can be changed into the following: minus 2 over a t psi t u square plus c over 6 t psi t u cube plus 1/2 t psi t psi t u square, right? We just play with the derivative. So what I have been doing is just trying to get the simple derivative form. Then we can integrate this over, right? Integrate. Minus a over 2 u square c over 6 u cube plus 1 over 2 t psi t u square equal to 0 again. We set the constant 0 again. Otherwise, it's just simple some a or b. trying to as slowly as possible. Again, we make a copy. Delete. The next page. Paste. So initially C was a constant. So let's set, we set C as 3A. So initially C is some constant we need to fix. So just to solve this equation, we set C is equal to 3A. So actually this was a fixed constant from the problem, right? A comes from theta x minus at, right? So A, actually we do not know what is A, and C is a given constant, so we can actually fix A, right? So here we fix A such that A is C over 3. Same story, right? So then minus 2 over A u square plus A over 2 u cube is 1 over 2 d psi du square. No. Plus equal to 0. Or minus A over 2 u square 1 minus u plus 1 over A 2 d psi du square is equal to 0. So what do we get? So d psi du square is A u square 1 minus u, or d psi du is square root of A u 1 minus u 1/2. So just playing with the derivatives, you arrive up to this point. Initially we have a bit complicated partial differential equation called the graph d3, which is about partial derivative with respect to time and x. This I remember. So d psi du A 1/2 u 1 minus u 1/2. Or u 1 minus u 1/2 du is xi, d xi. So actually we can integrate du u 1 minus u 1/2 is a xi. Again, we just put the constant to 0. There's a mosquito. It's much faster to be 0. He must be hungry, she. Let's say this is xi tilde. This integral. But I know the answer. It's one of the words in theory. How do I know this form? Don't ask me. There's another trick then when you take an exam or 수능 exam that you try something which gives you 0. So let's just try. I'll just stop here for now and let you it's actually a cheating because I know that this particular integral so let's do the opposite way. Let's try to take a derivative of the right-hand side. And it gives 1 over u, 1 minus u, 2. So I'm going to do this. d log 1 minus one half. So you can put this as something like an x. It's another chain rule, right? So what do you get? This is 1 over 1 minus u half. And du d 1 minus u 1/2, right? This is psi. So you probably by now you must be familiar with the chain rule. So 1 minus u 1/2. What do you get? We have minus sign, and du d 1 minus u half. One minus u 1/2 minus 1, 2, 1 minus u half, and du d1 minus u, right? Keep applying the chain rule, then you get 2, 1 minus u half, 1 minus u 1/2, and minus become just 1. I can make a copy of this. Copy. This is a very time-consuming problem. du equal. And likewise, du d log 1 plus 1 minus u 1/2. Same, right? You obtain the same thing. 1/1 plus 1 minus u 1/2, and du d 1 plus 1 minus u 1/2. And simply 2, 1 plus 1 minus u 1/2, and 1 minus u half. You got minus sign, right? So du d log 1 plus 1 minus u 1/2, 1 minus u 1/2 is simply 2, 1 minus u 1/2, 1 minus u 1/2. Minus become plus. 2, 1, 2, 1 plus 1 minus u 1/2, 1 minus u 1/2. Just a simple derivative, logarithmic derivative. All you need is patience. So let's do together. What do we get? We have a common factor, 2, 1 minus u 1/2, and you multiply this, 1 minus u 1/2, 1 plus, and what do we get? 1 plus 1 minus u 1/2, 1 minus 1 u 1/2, right? So if we combine these two fractions together, right? Fraction together, in Korean you say 통분한다. Then you multiply this. This is common factor. You just put common factor out, and you multiply by this and this, and then you they cancel each other nicely. And 2 also cancels with this, right? It becomes 1 minus u, 1/2, 1 minus u, right? So it becomes u, 1 minus u, 1/2 over 1. Familiar? Therefore, we know the answer, right? So if we integrate that, we have almost got her. Therefore, I will let you copy because. So I have chosen this example that partial differential equation, partial differential equation, no more difficult than solving some difficult percentage equations. If you know how to play with the derivative, this is one good example. And then we will try some more example, and then let's see if there is a systematic way of solving the equations. This is u. So now, therefore, u 1 minus u 1/2 du is log 1 minus u 1/2, 1 plus 1 minus u 1/2, which is psi tilde. Just we played with the derivatives and then integrate. You can further simplify. Psi tilde or 1 minus u 1/2. We still need to find the u, right? So 1 plus 1 minus u 1/2 is exponential tilde, right? So 1 minus u 1/2 is exponential tilde plus 1 minus u exponential e tilde. From log, we have exponential, right? So I just multiplied 1 minus this is this plus this. So therefore, 1 minus u 1/2 exponential tilde plus 1 is 1 minus exponential tilde. So 1 minus u to the half is 1 plus exponential tilde, 1 minus exponential tilde. You can divide numerator and denominator by exponential tilde over 2. Then we get this exponential minus tilde over 2, tilde over 2, exponential tilde over 2, exponential tilde over 2, right? This is what? Cosine hyperbolic tilde over 2 minus sine hyperbolic tilde over 2. Or 1 minus u is square cosine square hyperbolic over 2 sine square hyperbolic over 2. From this, u is 1 minus cosine hyperbolic cosine tilde over 2 sine hyperbolic tilde over 2 is cosine hyperbolic tilde over 2 cosine hyperbolic square over 2 minus sine hyperbolic square tilde over 2. What is cosine square, cosine hyperbolic square minus sine hyperbolic square? Equal to 1. This is equal to 1. Therefore, u is 1 over cosine square psi over 2, what is called secant hyperbolic square psi over 2. This is a traveling wave. This is one of the few cases that you can get the analytical solution for given partial differential equation. Therefore, you need to copy. Oh, so u psi secant hyperbolic square psi square over 2. Psi tilde is square root of a x minus at, right? The solution looks like this. This is 0. Or x equal 80. That means in terms of psi tilde, when this is 0, but that means x minus 80 is 0, right? Or x is equal to 80. So as time goes by, x is moving. So this is a wave propagating into positive x direction. This is a wave called solitary wave. Propagating in positive x direction. Solitary wave is sometimes called solitone. So perhaps you can take a break for 5 minutes. So actually it took almost 1 hour to solve one partial differential, nonlinear partial differential equations. Another example. So in many textbooks, the partial differential equation solutions are either written as a U or Z. So independent variable x and y. And solution z x y. So luckily we have only one derivative with respect to x only, right? So this is a probably simpler problem than the one we considered. So this is a typical case of a second order inhomogeneous differential equation. So for inhomogeneous differential equation, we can try step 1, homogeneous solution. Round x square, round square z minus y square z is equal to 0. Then, as we can lambda x lambda square minus y square equal to 0, lambda is plus minus y. So we can say homogeneous one solution is exponential yx, H2 is exponential minus yx. So second order differential equations, we play with the Wronskian, right? Here yx, here minus yx, y exponential yx, minus y exponential minus yx. So you multiply this first and then you subtract. So you get minus y exponential yx exponential minus yx minus y exponential minus yx exponential yx is minus 2y. Let's go back to some qx we start with yh1, yh2, yp equal u1 yh1 plus u2 yh2, right? Let me see, if I remember correctly, u1 is minus px Wronskian x sx yh2x dx, right? u2 px Wronskian x sx yh1x. Let me just check my notes here. Right, correct. So, if we go back to the original problem, partial x square, partial square z, minus y square z is equal to 0. Then zh1 was exponential yx, zh2 is exponential minus yx, Wronskian is minus 2y. So u1 is minus 2y, and sx was x square y square, and exponential minus xy dx, right? So 2 over y, x exponential minus xy dx. This can be put into the following: minus dyt, right? This is an integration about x, and you have x, right? Of course, you can integrate by using partial integration by part, but you can see that if you differentiate by y, you get x, right? So you can put minus dy over d in front of this integral, and this integral is y over 2 minus dy over d minus 1 over y, exponential minus xy, right? So it becomes y over 2 dy d y exponential minus xy is y over 2 minus 1 over y squared exponential minus xy minus y over x exponential minus xy. So this is 1, 2, 3. If we put them together, we get minus 1/2 over y plus x exponential minus xy. How about u2? u2 okay, 2 is Wronskian minus 2y xy square exponential xy dx is minus 2 over y x exponential xy dx. This time this is dyd exponential xy dx dyd y over exponential xy minus y over 2 minus y square plus y over x xy is 1/2 1 over y minus x exponential xy. So particular solution is u1 zh1 plus u2 zh2 is 1/2 minus 1 over y minus 1 x exponential xy exponential xy 1/2 1 over y x exponential xy exponential minus xy is minus x. So general solution is z some phi psi y x. Constant replaced by unknown function over y. So in partial differential equations, the general solution, in ordinary differential equation, we just have constant c1, c2, right? But now this is x and y. So instead of using c1, you can say some phi function of y, and psi function of y, and this is the pseudo solution. So far we have been relying on several tricks, but there may be some systematic way for solving this equation. So the general So we are talking about general nonlinear partial differential equations such as P, x, y, z, partial x, partial z, q, x, y, z, partial y, partial z is r, x, y, z. Here P, Q, R a given function. And this kind of equation has a name. It's called the Lagrangian equation. Lagrange's equation. So there is a mathematical theorem that is related to this. That is, we have the following theorem. If u, x, y, z is A and v, x, y, z, b are two independent solutions of an ordinary differential equation, given by dx over p, dy over q, dz over r, then there is an arbitrary function phi u v such that p partial x partial phi q partial y partial phi plus r partial z partial phi equals 0, and from this one can find z x y such that p partial x partial z plus q partial y partial z is r if and only if partial z partial phi is non-zero. This is a rather long theorem. Okay. So this is a general also the partial differential equation for C is a dependent variable x, y. So P partial x partial z plus Q partial y partial z is given by R. This is the name for the Lagrange's equation. And then how to find the solution? You need to solve this first. dx over p is equal to dy over q is equal to dg over r. And assuming that there are two solutions from this, u is constant and g is constant. Then there is arbitrary function phi of uv such that p partial x partial phi plus q partial y partial phi plus I partial z partial phi is equal to 0. And from this, we can find the z from the original equation. P partial z partial x plus q partial z partial z is equal to r. second condition, right? So let's start with phi uv. The partial x, partial phi is, you can use chain rule, right? Partial u, partial phi, partial x, partial u, plus partial v, partial phi, partial x, partial v. Partial y, partial phi, same. Partial u, partial phi, partial y, partial u, plus partial v, partial phi, partial y, partial v. Partial z, partial phi, partial u, partial phi, partial x, partial u, partial z, partial v, partial phi, partial z, partial v. Then let's see what happens. Partial x, partial phi, partial y, partial phi, partial z, partial phi. It's actually partial u, partial phi, p round x, partial u, q round y, partial u, r partial z, partial u, plus partial v, partial phi, p partial x, partial v, q partial y, partial v, r partial z, partial v, right? You just take a derivative. By the way, time to copy. I'll just wait for you. Now we found that this is 0, right? Because u and v are solutions of that, and these are 0, right? So what we get is missing page. I don't know how to delete this one. Oops. We have assumed that u, x, y, z equal to a, and u, x, y, v, x, y, z equal to b are solutions from dx over p, q over dy, r over dz, right? This is constant. So differential, what happens? So du, partial x, partial u, dx, partial y, partial u, dy, partial z, partial u dz is 0, right? Likewise, dv partial x partial v dx partial y partial v dy partial z partial v dz is equal to 0. Say this is lambda, what happens? Dx is p lambda, dy q lambda, dz is r lambda. Therefore, partial x partial u lambda p partial y partial u lambda q partial z partial u lambda r is lambda partial x partial u p partial y partial u q partial z partial u r are all 0, right? And likewise, and lambda partial x partial vp partial y partial vq partial z partial vr is equal to 0. So that means this is 0 and this is 0. So what happens if we go back? Oops. I think we have, therefore, partial p partial x partial phi plus q partial y partial phi r partial z partial phi is equal to 0, right? That's one of the conditions for the theorem. So we obtain this. And from psi u v is some constant surface. Let's take a partial x partial phi. This is psi x y z. Then partial x partial psi plus partial z partial phi partial x partial z is equal to 0. Therefore, partial psi partial x is minus partial x partial z partial psi. But likewise, y partial y partial psi plus partial z partial psi partial y partial z is equal to 0. That means partial y partial phi is minus partial y partial z partial psi. So if we substitute this into that, what do we get? Therefore, we have p minus partial x partial z partial phi q minus partial y partial z partial y plus r partial z partial phi is equal to 0. So if only if it's non-zero, we can divide from both sides, right? So we have p partial x partial z, q partial y partial z is equal to r. That's the original equation, right? Perhaps you can stop here today and continue next week.